Operating a sewage treatment plant starts not at the design load, but at a very low load. This is where real engineering begins. Most designers confidently explain performance at 100% design flow, but in reality, most sewage treatment plants operate at partial load, 20, 40, 50%, sometimes even much lower. And that is exactly where they fail. In this discussion, we are referring to continuous flow biological treatment plants, such as activated sludge process, extended aeration process systems, and the popular MBBR-based continuous reactors. The logic we discuss applies to any continuous aerobic biological sewage treatment plant. This presentation is not about an automated plant. It is about a manually operated plant that has been designed with some process intelligence. Let us face the ground reality. Most sewage treatment plants, be it ASP, extended aeration, or MBBR, are designed for full occupancy. But how often are these buildings fully occupied? Almost never. Yet, blowers run continuously, pumps run continuously. Maybe the pumps have float switches which go on and off depending on the incoming water. Operators blindly maintain MLSS targets. Failure rarely happens at overload. Failure happens during underload. And these are facts. Unfortunately, many designers do not design with flexibility because they lack understanding of real-time operations. For the sake of discussion, we are using 50% load as a reference, but understand this clearly. The logic applies to any underloading condition. It can be 70%, 40%, 25%. The percentage is not the issue. The imbalance is the issue. When load reduces, food reduces, but the biomass remains the same, which means MLSS is kept at design values. In ASP and extended aeration process, MLSS remains high. In MBBR, media biomass remains attached. Oxygen supplied remains unchanged. So, what happens? The food to mass ratio drops, or it is not as per design values. Sludge age increases in suspended growth systems. Biofilms become thicker and older in MBBR systems. Biological balance is disturbed. This is a universal process logic. What happens next? Microorganisms become underfed. They enter into endogenous respiration, which is eating themselves up. They start to die or exit the system. In ASP and extended aeration process, sludge becomes older, settlability changes. Foams may appear. In MBBR, biofilm thickens. Oxygen transfer reduces inside the film layer. MLSS may look healthy. DO may show good levels if you have a DO meter. But I think most of these plants may not even have a functional DO meter. But this doesn't mean that the plant is failing. But the logic of operation is what is failing. In a partially loaded reactor, we have assumed 50% volume. Let me also make few more assumptions. Let's assume the plant has two reactors or two compartments in reactors. We can operate only one reactor. If there is a single reactor, we can reduce the aeration duration. If the entire tank runs continuously at low load, you are overstabilizing biomass. Design without flexibility is not process design. It is infrastructure without intelligence. Let's understand the dissolved oxygen-based operational problem. This is where serious misunderstanding exists. Dissolved oxygen-based operation has been promoted as smarter control or even smarter operation. But DO does not measure biology. It measures dissolved oxygen water. In low load conditions, oxygen demand is not so high. DO naturally is higher. Operators see high DO and assume the system is safe. But high dissolved oxygen does not mean anything at all. It does not mean the biology is healthy. It means there is over-aeration. It may even mean that the sludge is aging. What happens when DO probes malfunction, which is commonly happening in almost all plants? What happens when they are not calibrated? What happens when the sensor reads incorrect readings? Blind reliance on dissolved oxygen-based aeration control has become one of the hidden reasons for instability in continuously operating plants. Blind reliance on dissolved oxygen-based aeration control has become one of the key reasons for plant failures. We are not expecting to have plants with VFDs and timer logics. We can have an observed timing, a few minutes on, a few minutes off of the blower. This itself is going to solve your problems that you would face in terms of sludge aging and so on. Other things to observe are odor. Observe the mixing. You can see the sludge behavior. And if everything looks okay, then probably the plant is also functioning okay. You still have the water to test. Look at the water, and if the water is clear, which means the treatment has worked. In activated sludge processes and extended aeration systems, there is something called a RAS pump. This pump continuously pumps water from the clarifier into either the collection tank or to the anoxic chamber. This also has to be tweaked during low load operations. If RAS is not reduced, MLSS increases, sludge retention time increases, sludge becomes too old. At partial load, RAS runtime must also be reduced proportionally. Sludge wasting must be disciplined, or sludge wasting should be adjusted. Sludge retention time control is real intelligence. MLSS chasing is only going to end you in trouble. Regardless of technology, extended aeration or ASP process, observation is fundamental. A simple 1 liter jar test in suspended growth systems can reveal the sludge health. Watch the clarifier for sludge blanket. This gives you an understanding of how the plant is functioning. Foam formation should be monitored. In MBBR, observe media movement, excessive biofilm falling out, color of the mixed liquor. Before analyzers existed, plants operated successfully. Today, with all the sensors, what we have is sensor failures, and many plants collapse. This is not automation failure. This is dependence without basic understanding of sewage treatment systems. Continuous flow biological plants require balance. At partial load, one must reduce reactor volume or supply of air, sludge recycling options, and sludge age. This logic applies to activated sludge, extended aeration, MBBR process. Automation can assist, but it cannot replace biological understanding. In a continuous flow biological treatment plant, at partial load, one must reduce reactor volume, oxygen supply, sludge recycle in ASP systems, sludge age. This logic applies to all the plants, be it activated sludge, extended aeration, or MBBR. One can use a DO-based operation control, but this is not a substitute for thinking. Operating a sewage treatment plant at under load needs biological understanding. We can use DO-based, VFD-based operations as a substitute for thinking, as a result of which failure becomes inevitable. I hope you understand reality. Thank you.